Right, welcome to the ninth lecture of Signals and Systems. Today we'll move into the next module of the course. ठीक है, पहला क्या था module?
Signal basics one.
Signal basics, right? So that was getting or familiarizing ourselves with the basics of signals. Yeah. Then we moved on to the second module, which was system basics. And in there, when we were discussing all those things, we saw a major subclass of signals and systems. We saw many, but one particular one we saw was continuous time versus discrete time. Yes, and when we were doing vocabulary, we also saw that processes or signals, even systems actually, can be represented in at least two domains that we know. We can represent them in time domain or in frequency domain. Okay, so from here your course will split according to that. So there is discrete time systems, okay, and continuous time systems. Yeah, and each of these can be represented in time domain and frequency domain. Same here, we could be working in time domain or we could be working in frequency domain. So from here on, we split the whole study of our course into two major groups, which is discrete time and continuous time, and then each one is divided into domains, and we will see each of them separately. So the way I like to work on it is to first do discrete time systems in time domain, okay, and after that we look at discrete time systems in frequency domain. Okay, and these are chapters 3 and 5 of your book. What we have done so far is mostly background and chapter 1. Okay, I spent a lot of time on that because it's needed. Yeah, but from here on, this is the bulk of your book, chapter 2, 3, 4, 5, 7 and 9, I think. And here what we do is, this is chapter 3, this is 5, this is 2, this is 4. Okay, so the way I teach this course is that I do 3 and 5 first, which is what? We will restrict ourselves to discrete time signals and discrete time systems. First we will look at them in the time domain, then we will see them in the frequency domain. Okay, हमने discuss किया था very briefly when we did the vocabulary what we mean by the frequency domain, Fourier, Laplace, and as such. We'll come back to that in great detail, inshallah. But for now, what is the reason for doing this? It seems in your book the continuous time comes first. Yeah. So the way your book goes is they do continuous time systems and signals in time domain, and then they do discrete time systems and signals in time domain. Then they come to the frequency domain. My reason for doing this is very simple. In discrete time, when we are dealing with discrete time systems, you are dealing with series. Yeah, summations होती हैं उसके अंदर, simple. Yeah? So if I give you, let's say, summation I is equal to 1 to 10 xn equals n, आप लोग बेहोश नहीं हो जाएंगे इसको देख के, right? So you can imagine, okay, this is a series, I can sum it. Yeah. When we are working with discrete time systems, we are dealing with series and naturally with summations. Yeah. But when we work with continuous times, we have to work with continuous summations. What's a continuous sum? Integral. Yeah. So this guy stretches out to this. It might be t to t plus n, xt dt सारे इंटेग्रल देख के सब परेशान हो जाएंगे, right? Similarly, in discrete time, often we will work with xn plus 1 minus xn kind of equations, yeah, equals, let's say, k. This we call a difference equation. In discrete time systems, you have summations and differences. Yeah, summation in continuous time replaced by integral. So can you guess what is difference replaced by? Difference equations होती हैं. What are they replaced by?
Division. Sorry, difference equation. Only one.
Differential.
Differential equation.
Yeah. So आप लोग जब पहली बार differential लिखा होगा तो xn minus xn plus delta divided by delta as limit delta goes to 0, यही किया होगा ना, वो derivative था ना. Yeah. So there you were already dealing with differentials. So you will have to work with differential. Now again, compared to that, this अक्सर students के लिए थोड़ा सा मुश्किल होता है. Now my goal is not to teach you summations series. तो आप कर चुके हैं, किस कोर्स में किया? रो धो के किया आपने किसी कोर्स में, कैलकुलस 2 वगैरह में या डिफरेंशियल किया ना, yeah? And without maybe knowing it, you have also dealt with differences. Yeah, simple है. You have done these also, but most of you find this slightly harder. Now my goal is not to teach you integration or differences or summation of series. My goal is to teach you how these represent signals and systems. Yeah. So I want to deal with the easier math when I'm developing the concept. You will notice once we have developed the concept in discrete time, either time domain or frequency domain, there is a very simple connection from there to here. Okay? जो कुछ हम यहाँ concept सीखेंगे, we'll just replace summations with integrals, differences with differentials. The concept will be 99%. कुछ छोटा मोटा change आएगा, but other than that, it will be exactly the same. So why not develop the concept with something that is easier for you to handle? Okay, so that's why I usually start with discrete time first. So I will do discrete time signal system in time domain. You will see lots of these guys, summations, series and their summations and their differences. You will not see any of these guys, yeah, but you will develop the concepts that I need to develop in this course. Yeah. Then we will develop those concepts in frequency domain, and after that we will come here. This jump will be very straightforward, and you will realize, okay, whatever we did, what concepts we developed there, the model of a discrete of a system, the response of a system, the, let's say, how to test the stability of a system, all those things, whatever we learned here, the concept is exactly the same, only the mathematics changes a little bit. Goes from discrete math, kind of discrete or this kind of math, series math, to continuous math. Okay, otherwise no big change. So the next two modules of this course are now going to be this guy, discrete time signals and systems in time domain, and this guy, discrete time signals and systems in frequency. Notice from here on we will study signals and systems together. पहले हमने उसकी basics अलग-अलग कर लिए, right? Now we want to, of course, signals and systems, they make sense together. अकेले कोई अगर एक system है, वो ना कोई input लेता है, ना कोई output generate करता है, कुछ भी नहीं है, उसका क्या करना आप? Right? So they go hand in hand. Yeah? The very basic black box diagram is this, very basic one. इससे भी आप काम कर सकते हैं. होता है एक सिग्नल सिस्टम सिर्फ जनरेट करता हो, या होता है एक सिस्टम सिर्फ रिसीव करता हो. ओके, सो इट रिसीव्स, डज इट एब्जॉर्ब इट और डज इट रिफ्लेक्ट इट? ऑप्टिकल सिस्टम है, लेट्स से. या सो very basic one we usually draw is this signal system. फिर आप इसको बड़ा करते जाते हैं, यहाँ भी सिस्टम लगा दें, यहाँ भी सिस्टम लगा दें, फिर सिस्टम्स को कैस्केड करना शुरू कर दें. रियल सिस्टम्स उस तरह होते हैं, राइट. वी विल study their smaller version, let's say their unit, smallest versions. जब आपको उनके concepts, once you are able to handle those concepts, going up is relatively easier. So let's start with our definitions again. So what is a discrete time system?
Where time is discretized into certain units.
System. Yeah.
Discrete signals को analyze कर.
Yeah. So if the input and the output are both discrete, याद किया मैंने define किया था ना? So it is defined by its signal. Discrete time signal आपको already पता है, right? So if the input and output of a system is discrete time, then the system itself is called discrete time. फिर हमने 4 क्लासेस पढ़ी थी, converters भी होते हैं, continuous time भी होते हैं. We saw that, yeah. Okay. So in discrete time, we will, instead of, we've been writing, a lot of what we looked at so far was actually in continuous. When we were doing signal basics, we were talking about xt, yeah, but I mentioned that we could also easily look at xn, yeah. So when you go study discrete time, instead of t we use n. Yes. Now if this xn is a discrete time signal, then what is n? It's a discrete valued variable. Yeah. So discrete values की क्या examples हो सकती हैं?
1 से 10, say 1, 2, 3, 4, 5, 6, 7.
Yes, fine. अगर 1 से 10 सारी values हो फिर क्या होगा?
दरमियान में भी ले लो तो continuous हो गया.
So gap चाहिए. Yes.
Gap.
It's the gap that defines it, right? So वो हम discuss कर चुके हैं पहले भी. Now how does the gap look like? From the point of view of discrete time system, that doesn't matter. Okay, the gaps could be large, the gaps could be small, but not infinitely small कि वो continuous बन जाए फिर. Yes, and the gaps could be uniform or non-uniform. There is no reason to imagine that a discrete time signal will be x1, x2, x3, 1 1 का gap जरूरी नहीं है. हो सकता है आगे जाके वो x3.5, x4, x4.5, तो वो non-uniform sampled हो जाएगा. Yeah. So basically we will use n. This is our discrete time signal. This guy is discrete, and by that we mean that it has some sort of gaps. For example, n can be integers, set of integers. Discrete time है, discrete है. Yes. So if they are integers, this would be x0, x1, x2, and so on. It could be even integers. That's also fine. So x0, x2, x3, x4, so on. Yeah. It could be odd integers. What else could it be? It could be 0.5k, where k is integers. Yeah. So it could be that your signal exists at x0, x.5, x1, x1.5. Yeah. Could be like that. It could even be, now all of these are uniformly spaced, right? So this kind of discrete time system, we say they are uniformly sampled. कि जो हर दो values हैं उनके दरमियान जो gap है वो uniform है. But there is absolutely no need for that to be the case. And in fact, we do work a lot with non-uniform. For example, let's say you have n equal 0.5, 0.6, then 1.0, 1.1, 1.5, so on. बीच में gaps change हो रहे हैं, right? किसी formula के तहत हो रहे हैं, नहीं हो रहे, depends. Yeah? But from the point of view of describing a discrete time signal, it doesn't matter. Uniformly sampled है, non-uniformly sampled है, doesn't matter. As long as there are gaps, this is a discrete time signal. Okay. So अब सवाल ये कि डिस्क्रीट टाइम आते कहाँ से सिग्नल्स? Where do we get those from?
हम जस्ट लेट्स से कोई डाटा कोई स्पेस से सैंपल कर रहे हैं तो डिस्क्रीट बन गया है.
So in nature, most phenomena are
Continuous time.
physical phenomena, at least mostly are continuous time, right? तो आपने जैसे कहा sampling, we create the discrete time version, एक ही है. फिर कुछ many of the say processes we deal with are naturally discrete. कोई example दे सकते हैं आप?
जैसे क्रिकेट में ओवर्स होते हैं.
ओके सही. रन्स हैं, आधा रन तो नहीं हो सकता, वो भी जाता है लेकिन फिर काउंट नहीं होता. राइट. सो some things are naturally discrete, like people are, number of people in household. आपने एक मैप बनाया है स्वाबी का, locations are the independent parameters and number of people in that location or in that house, so वो naturally discrete होते रहेगा. Number of students attending my lectures. अब lectures is not the number of students, वो तो है ही discrete, लेकिन lectures by nature are discrete. आज एक होगा, कल एक होगा, continuous तो नहीं करा सकता मैं, right? So
कभी आधा भी हो सकता
है आधा आधा लेक्चर हॉस्टल इन गैप तो होगा, राइट? और ये कंटिन्यूस नहीं चलेगा, राइट? सो duration of the lecture is a continuous variable, yes, but if I'm just counting, अगर आप चाहते हैं 2 दफ़ा अटेंडेंस लिया करो फिर वो भी पकड़ा जाए, लेकिन otherwise, so don't imagine that we always sample, okay? Yes, sampling is the most common way of getting discrete time signals. Temperature in the room, intensity of the light, humidity, these सारे processes, most natural phenomena are continuous in nature. We discretize them. ठीक है, क्यों करते हैं? क्या चेक?
उनके पैटर्न्स
कंटिन्यूस में क्या मसला?
वेरिएशंस बहुत आती हैं छोटी-छोटी.
कंटिन्यूस सैम्पलिंग कर नहीं सकते
हैं?
या कंटिन्यूस सैम्पलिंग बहुत मुश्किल
नहीं
होती है,
सैम्पलिंग
possible.
रिकॉर्डिंग तो आप कर सकते हैं
इसकी
ना.
जो डेटा माइनिंग है की आसानी रहेगी. डिस्क्रीट सिग्नल जब आएगा ना तो डेटा माइनिंग में एनालाइज करना आसान होती है.
ओके, गेटिंग क्लोजर, आप आगे चले गए माइनिंग तक, दैट्स गुड. बहुत बेसिक सी चीज़ है ना. क्या है
सर? कंटिन्यूस हम काउंट नहीं कर सकते ना.
जो हमारी सर्किटरी है ना मॉडर्न दौर की सारी, लॉजिक डिजाइन पढ़ा है ना?
बिट्स ओवर.
Yes, all of it works on continuous time system. Now, people tried the discrete time. लोगों ने इससे पहले जो continuous time computers बनाए हुए हैं, एनालॉग computers, right? याक का सुना होगा आपने, 1965 वाला जो है, क्या साइज था उसका? नहीं नहीं,
कमरा जितना
वो रूम में तो उसकी हार्ड डिस्क आती होगी. दैट वाज 3-4 स्टोरी का वेयर हाउस था, उसके अंदर वो रखते थे, राइट? सो यू कैन वर्क विद एनालॉग सर्किट. पढ़ लिया ना आपने, कुछ एनालॉग होते हैं कंपोनेंट्स. यू कैन मेक कंप्यूटर्स, सम कंप्यूटर्स विद एनालॉग कंपोनेंट्स आल्सो, पर वो जो एनालॉग होगा दैट टेक्स अ लॉट ऑफ स्पेस, उसकी प्रोसेसिंग इज अ हेडेक. दिस इज अ रेवोल्यूशन जो हमारे पास, जो डिस्क्रिटाइज्ड डिजिटल लॉजिक है, जो बूलियन लॉजिक आप पढ़ते हैं और फिर उसको इम्प्लीमेंट करना यूजिंग द लॉजिक गेट्स, दैट इज द ट्रू रेवोल्यूशन इलेक्ट्रॉनिक्स में, राइट? और उस रेवोल्यूशन, दैट होल रेवोल्यूशन इज बिल्ट ऑन डिस्क्रीट नंबर. उसमें कंटिन्यूस की जगह नहीं है, गेट ओपन है या बंद है, सही है? पार्शली कुछ आप कर सकते हैं, लेकिन अगेन कंटिन्यूस पे जाएंगे तो यू गेट स्टक. Okay, so now because of that we often discretize systems, पर हम सिर्फ discretize नहीं करते, फिर उसको digitize भी कर देते हैं. तो जो उसकी actual values हैं उनको भी discretize कर देते हैं. Then you go into this binary and those things, yeah. So why we discretize, or where the discrete time signals come from? Mostly by sampling, but not necessarily. There are processes, there are systems that by their very nature are discrete. उनको discrete करने की जरूरत नहीं है. But then there are a lot of phenomena that are actually, how many voice है? your mobile, if I'm calling someone, the mobile collects my voice. My voice itself is a continuous phenomenon, ठीक है? But जो मोबाइल है वो उसको पहले डिस्क्रीटाइज करता है, डिजिटाइज करता है. Then all the circuitry in the mobile, जो आपकी चिप है, that is working on discrete numbers, yeah, digital processor है वो. Yes, the digital processing happens, and then अब बताइए जो फाइनल इसमें से सिग्नल जाता है फिर वो क्या है? डिस्क्रीट है, कंटिन्यूस?
डिस्क्रीट
डिस्क्रीट जाता है,
कंटिन्यूस है.
नहीं बल्कि
क्या जाता है? फिनोमिना क्या है?
जो भेजते हैं जो निकलता है
इसमें से जो जाएगा, अब
स्पीकर से जो निकलता है.
एक सिग्नल कॉल में कर रहा हूँ, लेट्स से आई एम टॉकिंग, मेरी वॉइस इसके अंदर डिजिटाइज हुई, प्रोसेस हुई, अब वो थ्रो होनी है टू द बेस स्टेशन जहाँ भी वो लगा हुआ है. वो कैसे थ्रो होती है? ईंट पे बांध के फेंकते हैं क्या करते हैं? रेडियो वेव्स है. रेडियो वेव्स क्या होती है? कंटिन्यूस होती है, बैक टू कंटिन्यूस. इसका मतलब है कि ये जो डिस्क्रिटाइज करना ये हमारी मजबूरी है. एक्चुअल तो फिर दोबारा उस पर जा रहे हो आप. उस जो बंदे ने फाइनली सुनना है, उसके स्पीकर ने जो जनरेट करना है इवेंचुअली, वो फिर नहीं कंटिन्यूस हो जाएगा ना, आवाज़ है ना उसने सुननी. तो ये जो बार बार डिस्क्रीट पे जाते हैं हम डिजिटल, ये हमारी मजबूरी है. अगर कभी आपने कोई ऐसे कंपोनेंट्स निकाल लिए जो कंटिन्यूस में उस तरह काम करते हैं जैसे डिस्क्रीट में हमारे पास डालें, तो चीज़ें और भी तेज़ हो जाएंगी. ठीक. सो we normally discretize. Okay, so the process that we just described, I just want to draw it for you, so you know, because it's not enough to say okay we are working with, आप कहते रहिए मैं discrete time system, कोई आपसे पूछ ले आते कहाँ से और आप हक्के बके रह जाए, that's not good learning, right? You should know the origins of things. Heroes की back story सबको पसंद होती है, villains की भी पसंद होती है, so you should know the back story also, because that develops, ये सारे कॉन्सेप्ट्स को फिर वो जोड़ देता है. अब आपको लॉजिक डिज़ाइन कोर्स अगर आप पढ़ चुके, आप दोबारा से अगर देखेंगे उसको तो एक नई इंस्पिरेशन के साथ देखेंगे कि इट्स नॉट जस्ट लॉजिक डिज़ाइन, इट्स नॉट जस्ट बूलियन अलजेब्रा, ये एक रेवोल्यूशन है. या ट्राई कर लें अभी इस दौर में भी, इफ़ यू वांट टू डिज़ाइन एन एनालॉग कंप्यूटर, वो अभी भी इस कमरे जितना हो जाएगा, राइट? क्योंकि उसमें वो जो चीज़ें लगेंगी ना, वो उसका आप कुछ कर नहीं सकते. You can do basic mathematics with simple circuits. छोटी मोटी एडर सब्ट्रैक्टर बनाए आपने कुछ सर्किट्स वगैरह से, आप विदाउट यूजिंग ऑप एम्प्स वगैरह यू कैन ट्राई दैट एंड इट कैन वर्क. डिवाइडर होता है ना, वोल्टेज डिवाइड हो जाती है, दैट इज कंटिन्यूस. सर करंट जा रहा है, डिवाइडर में आधा करंट इधर भेज दिया, आधा हो जाता है ना, कंटिन्यूस है. और उस डिवाइडर से आप वो 1 बिलियन डिवाइडर्स बनाए रजिस्टर से, comes a headache. There comes binary logic, digital logic and the semiconductor. Yes, so ये जो सारी चीज़ें आपको पढ़ाते हैं ये सब connected है. It depends आगे आप किस चीज़ को use करते हैं. So now usually this is how things go. Usually you have a continuous phenomenon like my voice. You put it through a system and you get a discretized version of this. Yeah, अभी मैं digitizing पे उतना नहीं जा रहा क्योंकि वो भी एक स्टेज होती है, but let's be more interested here. So what is this system? ये किस इसकी क्या क्लास होगी सिस्टम की? Is it a discrete time system, continuous time system?
Neither. ADC.
कंटिन्यूस
किया था ना हमने,
एनालॉग
वो एनालॉग पे नहीं आ जाए, डिस्क्रिटाइज कर रहा है बस, ये डिजिटाइज नहीं कर रहा.
डीसीसी.
Yes, so the most common name is C to D converter, continuous to discrete converter. Yes, so this system is a converter. Then often we work with some discrete time systems. In fact, we further digitize and we work with digital systems. Yeah, but इस course के लिए वो जब आप अगर कोई course होता है digital signal processing or communications, there we focus more on that. For our purposes, it's enough to stay here. It processes and gives you some discrete time output. So by definition, discrete in, discrete out. So the system is discrete time. We define किया था ना हमने by its input and output. Right. then it goes back to continuous time yt. Yeah, so what's this system now?
DCC.
Yes, so discrete to continuous converter. Yeah, हम इन कन्वर्टर्स की डिटेल्स में नहीं जाएंगे. दैट इज द कोर टॉपिक्स फॉर सर्किट एनालिसिस एंड अदर कोर्स इन इलेक्ट्रॉनिक्स. या और DSP में भी आता है, लेकिन here we are sticking to signals, but we need to know what happened. So this was kind of my voice. I said something, hello, and it was discretized. Yeah, we discretize होगी, sampler लगता है अक्सर. We don't go into how the sampling occurs for other courses. Yeah, वो उसके वो topics हैं. Sampling happens, processing happens, it is changed a bit. Why do we change? क्यों change करना चाहेंगे हम कोई within the system?
Maybe you'll want to edit it some way, maybe make it faster or something.
Amplify
WhatsApp में हम
the-
times 2 कर रहे.
Amplifying कर. अब देखो ना, what I'm saying is, what I say to my friend, इसने और उसके मोबाइल ने और बेस स्टेशन में चेंज तो नहीं करा ना, है ना? मेरा हेलो मैं बाद में कॉल करता हूँ, वो कह रहा नहीं मैं नहीं करूँगा. चेंज तो नहीं करना उसने, राइट? तो फिर क्यों प्रोसेस कर रहा है? क्या जरूरत है? What's the need?
कभी जगह आप एम्पलीफाई की
एम्पलीफायर की बात हुई जैसे, राइट? सो एम्पलीफाई क्यों करना चाहेगा वो उसको?
लॉसेस
टू प्रोटेक्ट इट. इसको पता है कि आप इस आवाज़ ने जिस इन्वायरमेंट में जाना है, वो इन्वायरमेंट में इंटरफेरेंसेस आएंगी, उसमें मिटिगेशन आएगा, सिग्नल वीक होगा, तो ये उसको प्रोटेक्ट करने के लिए उसकी बहुत सारी प्रोसेसेस उसके लिए शेल्स लगाएगा, पैकेट बनाएगा उसका, राइट? फिर उसको थ्रो करेगा. ऑल्दो अगर आई कुड शाउट आउट टू माय फ्रेंड तो बेस्ट होगा, right? But we cannot do that, we need to use this. So it's not always that you want to change the signal. You also often want to protect it, encapsulate it, encrypt it. Encryption भी होती है, WhatsApp पे लिखा होता है कि आपके Z messages सारे point to point encrypted है, right? So the encryption itself is a digital process here. So after that, a lot of what we want as humans is like this voice thing. वो फिर दोबारा क्या हो जाता है? Continuous time. अब आप अपने दोस्त की आवाज़ तो जाहिर है ये जो स्पीकर जनरेट करता है, ये क्या जनरेट करता है जब वो सुन रहा है? स्पीकर जनरेटिंग साउंड वेव्स. Continuous time phenomena आ गया, right? It's actually compression and rarefication of the air around you. Yeah. So sound waves generate करता है ये. Those sound waves are again continuous, and of course the idea is that it should be, unless you want to really change the voice or something, it should be the same. Yeah. In और cases में और होगा, लेकिन the process is like this. Eventually you want this thing, but now let's stick to just my mobile here. Yeah. Let's say we haven't reached my friend yet. This is my mobile. It took my voice, discretized it, processed it, क्या किया उसको encapsulate कर दिया, encrypt कर दिया, digitally सारा कुछ कर दिया, ठीक? Now it's going to throw it into the environment as a radio wave. Yes. So discrete time दोबारा कैसे बनेगा यहाँ पे? Continuous time कैसे बनेगा? क्या होगा?
सही कन्वर्टर.
Right. So how would it look?
Sir,
पहले वाली
वो है जब my friend listens to it, the other end. Yeah.
वो भेजेगा.
सर लेकिन अगर आप उसको encrypt कर रहे हैं तो इसमें एक और सिस्टम नहीं आना चाहिए जो उसको बाद में decrypt भी करे?
I'm just exactly वो तो the receiver mobile. ये this is all my mobile now.
ट्रांसमीटर.
लेकिन यहाँ से जो आप कह रहे हैं कि वो साउंड वेव वैसी ही जाएगी जैसी थी वो वैसी तो नहीं
नहीं
जाएगी.
वो मैंने अब change कर दिया ना. We were first saying okay it's the whole system. Now I'm saying it's just my mobile. Right? So now some waves will have to go from here. Right? वो जब वहाँ पे जाके उल्टा process उसके साथ होगा फिर ये निकलेगी दोबारा. Right? So this is now the transmitting end only. Now the question is how can a continuous can convert into discrete sampling से? Simple समझ आती है आपको, कोई मसला ही नहीं उसमें. राइट? आप एक सैंपल लें, फिर दूसरा लें, गैप के साथ फिर तीसरा लें, वेरी इजी. हाउ डज डिस्क्रीट बिकम कंटिन्यूस?
सर आप दो जो गैप होता है उनके दरमियान ना आप बस एक लाइन मार देते हैं.
लाइन मार
दो बस.
ओके, एनी अदर थॉट्स? सो आप सोचें, मैं बताता हूँ फिर कैसे वापस कैसे जाएंगे.
बहुत अच्छा सवाल है.
बहुत अच्छा सवाल है ना?
अच्छा सवाल
नहीं,
है.
इतना इजी नहीं है ना. आपने रेडियो फ्रीक्वेंसी, रेडियो वेव्स फेंकनी है ना, right? This mobile is going to throw radio waves, yeah. So that is where the again the discrete systems come in. I don't know, आपने कहीं पढ़ा है, यानी कोई मॉड्यूलेशन पढ़ी है आपने? फ्रीक्वेंसी मॉड्यूलेशन, एम्पलीट्यूड मॉड्यूलेशन
हल्की सी है.
हल्की पढ़ी है. फ्रीक्वेंसी मॉड्यूलेशन पढ़ी है, yeah. So what we do is basically we say, okay, we usually have a mapping from a discrete time thing to a continuous time thing. For example, we'll say, okay, I will generate a frequency for, let's say, 1 millisecond or 1 microsecond. Continuous frequency, radio मेरा जो एंटेना है ना इसका, that will generate this frequency for 1 millisecond, and this frequency will be somehow dependent on the height of this guy. ठीक है? So if it is low, I will generate a low frequency for 1 millisecond. If it is high, I will generate next वाला क्या होगा, slightly sorry, frequency high करनी है, yeah. So slightly higher frequency for the next 1 millisecond, and so on until this whole thing is translated into a continuous time signal. अब ये each burst itself is continuous, radio wave है, right? So this again shows you the need for digitizing. अगर यहाँ पे आप हर वैल्यू अलाउ करें तो कितनी आप जनरेट करेंगे, कितने आपको सर्किट बनाने पड़ेंगे, right? But if you limit it to 8 levels, then you have to generate only 8 kind of frequencies, right? So that's where the power of digitizing comes in. ना सिर्फ x एक्सिस को हम डिस्क्रिटाइज करना चाहते हैं, y को भी करना चाहते हैं, ताकि हमारी सर्किटरी लिमिट हो जाए, वरना तो हर एक की अपनी वैल्यू होगी, क्या करेंगे, रेंजेस बनाएंगे, क्या करेंगे. So but notice now, from here this will be sent, which will be changing frequency depending on the original. Now दूसरे एंड पे क्या होगा, जो रिसीवर है, मेरे फ्रेंड का मोबाइल है, उसने क्या रिसीव करना है. Now if I draw this for his mobile, they will receive this thing. तो उसकी जगह ऊपर टॉप पे क्या आ जाएगा, ये आ जाएगा, या क्या है ये, continuous time. Yes, his mobile will convert that into discrete time, process it. क्या process करेगा, decrypt कर लेगा फाइल कर लेगा, पैकेट जो उसके एड्रेसेस डलते हैं, कुछ काफ़ी लंबी डिटेल है वो, या बट वो सारी का मकसद क्या है, टू प्रोटेक्ट इट. या आपका TCS का पैकेज आता है, लेट्स से, या आपने मोबाइल मंगवाया, ऐसे तो नहीं आता. पहले मोबाइल की पैकेजिंग होती है, फिर उसके ऊपर TCS की पैकेजिंग होती है, उसके ऊपर लेबल होते हैं, किसका एड्रेस है, तो प्रोटेक्शन भी हो रही है और एड्रेसिंग भी हो रही है. सो अ लॉट ऑफ दैट वी हैव टू डू, बट ऑल ऑफ दैट हैज टू बी रिप्ड अपार्ट. माय फ्रेंड डजंट केयर, राइट? उसे तो सुनना है कि आ रहे हैं कि नहीं आ रहे. Yes, so all of that has to be ripped apart. So this continuous time will come here in his mobile now. Yeah, it will be converted into some discrete time. That discrete time will be processed to get rid of all the extra things that were there, and maybe to remove noise also. Big step. Yeah, noise will remove होगा, and that will again be converted into क्या होगी, sound waves, vibrations of your speaker. तो फ्रेंड का स्पीकर है, उसकी vibrations finally they will generate the final step from discrete to continuous. sound waves बनेंगी, वो sound waves का पैटर्न वही होगा जो बात मैंने बोली है, उसको जनरेट करेगा, राइट? और that will
सर अब जैसे जब हम डिस्क्रीट सिग्नल को रेडियो वेव में कन्वर्ट कर रहे थे, तब तो हमने ये मॉड्यूलेशन कर ली, ठीक है. लेकिन लेट से जब हमने साउंड वेव लेट से कोई डिस्क्रीट सिग्नल को साउंड वेव में कन्वर्ट करना है, उसको आप किस तरह कन्वर्ट करोगे?
तो
उसमें तो मॉड्यूलेशन समझ नहीं आती।
उसकी मॉड्यूलेशन नहीं समझ आती। स्पीकर फिर आप सही है, थोड़ा सा गूगल करें।
ये एम्पलीट्यूड
Again it's you have to go into how does an electronic speaker work. उसके अंदर करंट की ऑसिलेशंस हैं, those oscillation make some sort of oscillator होगा उसके अंदर कोई जो
Current
एक्चुअल
modulate
फिजिकल करेगा या करंट से
modulate.
आप उसको एक्चुएट कराएंगे। अब यहाँ पे दिस हैज टू जनरेट अ फिजिकल प्रेशर इन द एयर, साउंड वेव बननी है ना, तो वो तो उसका बहुत सिंपल सा आंसर है, जस्ट रीड हाउ ए स्पीकर वर्क्स, राइट। उसको आप करंट्स की वैल्यूज चेंज करते जाएंगे, वो दैट दिस इज नॉट एन एग्जैक्ट रेप्लिका ऑफ माय वॉइस, एग्जैक्ट नहीं होती है, या अप्रॉक्सीमेट जनरेट होता है ना, बट गुड इनफ यूजुअली, या सो unless you're putting filters on it on purpose. So although this is not directly related to the topic, but I believe that when we do something we should know, इससे थोड़ी सी पहले की बात, उसके इर्द गिर्द की बात, ये चीज़ें आपको पता होनी चाहिए। They really help you see things in a bigger perspective. Yeah. Otherwise, actually, I could just start by saying X1 is discrete and let's start solving problems. Yeah. So okay, so now you know this whole cycle, and by of course this is not the whole cycle actually. Actual if I wanted to draw this thing, इसके तो पूरे पूरे चैप्टर होते हैं किताबों के अंदर ना, सिर्फ सिंपली सैम्पलिंग के, फिर उसकी जो इंकैप्सुलेशन है, ऑल ऑफ दैट I wanted to give you a higher level idea. Now, how do we define energy and power in discrete time? So I have already given you definition of energy of a signal and power of a signal. Yes. So किसी को याद है energy की क्या definition थी?
integration of the square of the signal from
Integration of the absolute square.
Modulus.
absolute square.
Modulus.
Yeah. So the area under the absolute square of the signal. Yeah. So you had this thing was the energy.
Modulus.
Yes, absolutely. Yeah. dt. Yeah. So that was written generally for say continuous or so. But what if you're dealing with discrete time? What's your guess for a discrete time signal? Well, how would this change?
सर बस इंटीग्रेशन की जगह समेशन है।
Integration की जगह summation आ जाएगी, x n square, और n is minus infinity to infinity, and we already know by assumption that n is not continuous, it is discrete. अब वो कैसे discrete है, we don't care. Uniformly है, non uniformly है, big gaps हैं, small gaps हैं, gaps change हो रहे हैं, doesn't matter. Yeah, this definition holds. So what just happened, we rewrote the definition of energy of a signal from continuous time to discrete time signal. Yeah. So and you will find that usually this is easier to calculate for you guys. Remember, chance samples they do, it's just a series का sum है. Yeah. Similarly, what was the power of a signal? Continuous time में क्या थी power?
1 over t. Limiting 1 over t.
Limit 1 over t naught and
अंदर आएगा x.
इसमें था x t square, वही है चीज। लिमिट किस चीज पे थी?
सर ये नॉन पीरियोडिक, जो पीरियोडिक होते फिर लिमिट हट
Yeah,
जाती
but limit क्या थी? Limit t naught
T
goes
naught
to
infinity.
infinity. This was it. So what's your guess for this guy?
Summation.
Sorry, power for a discrete time. Limit तो होगी. Yeah, this will become
Summation.
summation, and then you will have to see, okay, you will have to sum it from sum capital N to minus of capital N to small n, x n absolute square, and this will be क्या होगा यहाँ पे? लिमिट तो होगी, लिमिट n goes to infinity, that's fine. यहाँ क्या होगा?
1 over n.
So if you assume that this is uniformly sampled, then it will be 2n plus 1. Okay. But if you don't assume that, then you'll have to adjust it accordingly. जितनी other terms हैं उतने से डिवाइड होना होता है. Integral makes sure of that by being continuous, वो तो manage कर लेता है. Because see, it was dividing by t naught. What is the range here? Minus t naught to by t naught is t naught. वो तो हो गया था. Discrete time में it becomes a bit complicated in the sense that okay, we know that we have to divide by the number of terms that are here. Now if this is uniformly sampled, you can tell that the number of terms is 2n plus 1. Why?
तो माइनस n की ले लो, जीरो डाल दो दरमियान में, तो वो कहलाता है.
Yes, so this is uniformly sampled as integers, yeah. So but it can change as long as you understand what's going on. Continuous के लिए क्या, sorry वो skill periodic का क्या था? So what was the definition for periodic?
उसमें limiting field limits field नहीं होता.
Yeah, that's power, yeah. But how did we define if a signal was periodic?
X
in time?
t plus t naught.
T naught for.
और
So if you can prove that there exists a T naught such that you have these notes, slides वगैरह वो सारा print आपके पास ना, जो YouTube किया है उसमें description में जाएंगे तो वहाँ पे ये इनका scan पड़ा हुआ है. I just download that 300 pages and PDF के. So but if you want to note it, it's fine. मसला नहीं.
सर पूरा कोर्स
The course पड़ा हुआ है.
कॉपी.
And you can replace me easily if you like. अगर आप लोग ताउन करें तो हम ये रोक सकते हैं. अच्छा. तो वो एक आई डोंट नो जोक आपने सुना है नहीं कि एक बच्चा मैट्रिक का रिजल्ट लेके आता है ना, तो वो अबू पूछता है कैसा था, तो कहता है कि आप जब मैट्रिक में फेल हुए थे तो दादा जान ने क्या किया था ना, तो उन्होंने कहा जी मुझे खूब मेरी पिटाई की थी. तो अगर वो जब फेल हुए तो उनके अबू ने क्या किया था, मैंने डंडों से मारा था. वो हर जनरेशन में थोड़ा
ज़्यादा हो जाता है.
कहता है अब्बा जान अगर हम दोनों ताउन करें ना तो ये वैश्याना रस्म. Right, so if you अगर आप लोग
सर ये ट्रेडिशन क्यों नहीं तोड़ देंगे, मैट्रिक में फेल नहीं होना.
बस वो तो अब हो गया ना बेचारा, वो वही कहेगा. अच्छा, so where were we? What do you expect in discrete time? It should be xn. If you can show that there is some n naught, so that for all n it holds, then you say that the discrete time process is periodic. Yeah, and the period would be n naught. Okay, so जैसे इसमें period पे क्या था for a periodic signal, what was the power? As you said, it was over one period, right? So limit की जरूरत नहीं रहती. Yes, you take one period and you integrate over that. Similarly for discrete time, that is how it changes. If you know that this discrete time signal is periodic with period capital and not, then you can simply write it as Px equals 1 over n naught, which is the length of the period, summation x n absolute square. Here you have to write over one period. Okay, so the indices are hard to write for discrete time if you don't know the exact period कि क्या है वो, because it could be कहीं से भी शुरू होते हैं भी जा सकता है. So for convenience we just say you take one whole period, sum up all the values in that one period, absolute square उनका sum कर दें, divide by the length of the period, and that is your easier case compared to using a limit.
0 से n naught का लिख सकते हैं वैसे.
लिख तो सकते हैं आप. बिल्कुल, you can write that. So हो गया ये. Now what else did we do? Signals में operations किए थे हमने, right? So if you remember क्या थे operation? Left shift, right shift. Yes. So what were they? Now what I'm doing is basically the things we did in signal basics in continuous time. I'm just repeating that in discrete times just for completion's sake. कोई उसमें conceptually कुछ नया नहीं है. So you have x n minus m क्या होगा इस m is positive number, क्या होगा राइट शिफ्ट हो जाएगा, ठीक है, जस्ट लाइक द कंटिन्यूस केस. और इसी तरह xn प्लस m क्या होगा लेफ्ट शिफ्ट हो जाएगा, ठीक है. एंड ऑफ कोर्स m आल्सो इज एन इंटीजर. ये क्या करेगा,
वो कर देगा
स्केल
वो करना
वर्टिकली फ्लिप कर देगा, सॉरी हॉरिजॉन्टली फ्लिप कर देगा, हॉरिजॉन्टली फ्लिप
y मिरर सॉरी x
इसमें याद करो इसको
Yeah,
हॉरिजॉन्टल
इसको
कहते
x
इसमें
मिरर
यही करते
वही
हैं।
ना।
एंड में वही है कि वो कर दे.
वो कर देगा
राइट. ओके, मुझे भी याद नहीं आ रही. दिस इज
ये वो करेगा
ये हॉरिजॉन्टल.
ये सब हॉरिजॉन्टल
Horizontal.
वर्टिकल ऊपर
मैंने
नीचे
क्विज में horizontal
So
बोला,
okay, then let's do
X
that
में
one.
क्या
ये क्या होगा?
ये
वर्टिकल के बजाय horizontal कर
ठीक है?
देता हूँ ना क्विज में.
So you you know that, that's fine. As I said, sampling was our way of getting discrete time signals, or let's say the most common way of getting them. So let's see how it works. Let's say you have a continuous time signal going like this. Continuous time है, voice, light intensity, humidity, will be temperature, all that before you actually record it. Now one common way of getting a discrete time signal from it is to sample it. Yes, so what do we do? I'm going to do this because we need to do some nomenclature. So this is xt, yeah. Suppose I decide to sample it after every capital T seconds. Unit कुछ भी ले सकते हैं आप, but convenience I'm going to say T. So I'm going to sample it after every T seconds, yeah. You could write TS here if you like sampling time. So let's say I start at the first sample is here. I collect this guy, yeah. Then I will wait how long?
ts
T or TS, yeah. And then I'll collect the second sample. Then I'll wait another T.
फिर डिस्क्रीट में भी कर रहे हैं
Discretize
Sampling.
करना, right? Sampling करना. Here, here, here. So this is time 0. This is time capital T. This is time
प्लस 1
2t
2T, 3T, 4T, and at let's say here it will be NT. And sample will be NT. Yeah. Now if I write out this signal now, I can write it as, let's say, if I want to write these values, how are they? Now it's a series. Yes, I'm going to write that series. What's the first value in the series? X0. Yes. What's the second value in the series?
so free
X of capital T. What's the third value? X of 2T, and so on, X, N, T, and if it want to go on, that's fine. Right? So now this is where a jump comes in our notation. Okay? What we usually do is we skip that capital T. We skip in our notation, we skip the sampling time, and we represent this as x0, x1, x2, and xn. Okay?
we just index it sort of
Huh?
indexing
T is an index now. It's just an n is the index. But what you have to keep in mind is that it's not it alone. It has no meaning. It's not the actual time. N पे क्या time चल रहा है?
you don't know
If you know that
If you know T,
if
then
it's
you-
uniform sampling and the sampling
T.
time was Ts, then what is the time at n?
n into t
ये लिखा हुआ nt चल रहा है ना time. This is the actual time, right? 1 second, 2 seconds, 3 seconds, 4 seconds. Yeah. Now what if I had chosen to sample every 0.5 seconds? So let's see, then nth sample पे क्या time चल रहा है?
0.5
n by 2, yeah. So because or n times 0.5, which is n by 2, yeah. Now the thing to remember is that in reality the continuous time signal is this, the samples are here, yes, and we usually write it like this, yeah. So whenever somebody gives you a set of discrete samples or says this is a discrete signal and they say x0, 0th value is this, first value is this, what should you ask for? First thing,
sampling time.
sampling time, okay. So this is very critical. A discrete time signal is incomplete without the definition of its sampling time, okay. क्योंकि यहाँ से आप नहीं बता सकते कि 1 second है. For example, if t is 1, x1 is 1 second, yes, fine. But if t is 0.5, x1 is actually happening at 0.5 seconds. It's not happening at 1 second, right? So you always need to ask what is the gap between these guys. And again, if it is uniformly sampled, then only one value is enough, which is capital T. If they say it's non-uniformly sampled, then you need to get the exact map, what kind of formula is being used for the non-uniform sample. फिर आप बता पाएंगे. But in this course, mostly we stick to uniform sample. Yeah. So there, all you need to do now, if I give you these values and I tell you that my sampling time was ts, now you know everything. Why? Because now you can tell me exactly when x2 happened. It happened at 2ts. This guy, right? This guy happened at nts, whatever that value is. Okay. So it's important to keep in mind that what you have in the brackets here is actually an index. It's not a true time. Actual time नहीं है. ठीक है? It's just an index. So then how can I write, let's say if I want to write xn in terms of xt, क्या लिख सकते हैं यहाँ पे? डिस्क्रीट को लिखना है कंटिन्यूस की टर्म.
n into t.
So I will say it is xt, but t equals n t. ये है जो आपको ज़हन में रखनी है बात. It's not खुद से ये, it doesn't mean anything alone. Yeah, it's a sample picked from the continuous guy at n t time. Okay, whatever that time comes out to be. Why does that help us? Basically, that means we are not bound to. If we say x0 and then we have sample x1, that doesn't mean we are forced to have a 1 second gap between them, right? क्या gap रख सकते हैं आप? कुछ भी रख सकते हैं. Sampling time कम करते जाएं, gap कम होता जाएगा. So if you make it 1 millisecond, then the gap will be a millisecond. Microsecond कर दें. It's up to you. So the gap between the samples can be adjusted based on the sampling time, and that is something we do. Now, okay, so I'll just mention 2 more operations and then we can stop. So we will go to the next part later. आपने वो हमने किया था जब when you did if you had xt, what was x2t? Compressed version of xt. Yeah?
Decompression है.
Decompression, yes. Now in discrete time systems also we often need to compress. Now if you have access to this thing, to the original signal, you can simply, let's say, change the sampling time. But if you don't have access to that, then compression occurs very simply like this, that you drop alternate samples So आप compression का तो काफ़ी सुनते होंगे processing में. Let's say you have xn is you have it at x0, x1, x2 and so on. Let's say it is x3, x4. Now often we need to downsample. आपको दे दिया जाता है कि this is the discrete time signal, this is the sampling time. Okay, now downsample it. If you have access to the original continuous time signal, then you can directly downsample. Just double the sampling time. The number of samples कम हो जाएंगे उस time के अंदर. But usually you don't have access to that. The only access you have is this time. ये already sample हो चुका है. अब इसको downsample कैसे करेंगे?
Let's say you have to half.
Let's say half करना है इसको.
So let's say if
और
it has
दूसरी
if
value
it has
का-
100 values, you can do
Drop
50.
करते जाएं बस.
Yeah, drop
Right?
values.
So drop every other value. Sort of आपने sampling time double कर दिया है. यही है ना? So you drop every other value. What you get? Let's call that the x downsampled n. उसकी values कैसे लगेंगी? x d0 is here. इसकी second value क्या होगी? x d1. Again it's an index. Yes, actual one नहीं है. So यहाँ कौन सी value आएगी?
X2 है.
x2. So x0 gets this, x2 gets this, xd2 में क्या आएगा? 3 तोड़ गया ना? 4. Yeah, and so on. Yes, and if you want to write it in general terms, क्या आ गया formula इनका आपस में?
XD would be x n plus 2. No wait.
वो तो shifting नहीं हो जाती?
टू
2
एन
end.
टू एन कंप्रेशन हो.
So it's back to वो जो हमने पढ़ा था. Yes, वही था ना? 2t was compressed version, though by a factor of 2. So you see that happening here. This guy is 2n. xd0 is x0. xd1 is x2. Yes, xd2 is x4. Yeah, and so on. So basically what I want to show is that this formula still holds. Yeah, and this is how you do compression. Now sometimes you are asked to upsample and you don't have access to the original. Again, why am I saying the original? See, if you had access to the original, you won't need to do this. आपने किसी ने ऐसे sampling की है, right? This is the way they sample, and they want you to downsample it. Now, if you have access to this original signal, all you can do is say, okay, I won't sample every t, I will sample every 2t, and I get a downsampled version. Yeah, fine, case close हो गया. Similarly, if somebody sampled like this, and they are asking you for an upsampled version, meaning more samples within that. Now, if you have access to t, okay, reduce your sampling time to half of that, for instance, and you can have more samples here. But now there is the problem. Often the data you are working with has already been discretized. You don't have access to the original phenomenon. क्योंकि ह्यूमिडिटी आपका इंतजार तो नहीं कर रही एंटार्क्टिका में, राइट? किसी ने डेटा रिकॉर्ड कर लिया 10 साल का, 5 साल का, 10 दिन का, आपको भेज दिया डिस्क्रिटाइज करके. अब आपको ख्याल आई नियर आई नीडेड मोर सैंपल्स और अप सैम्पलिंग की जरूरत थी, राइट? सो व्हाट डू वी डू? क्या करते
You
हैं
could do two things. One thing is you just can't do it. In like a good example is in photos, when you have a compressed photo, you can't exactly make it a better resolution photo.
हम?
And another way is that like you can use AI or predictive upsampling, I guess.
Yes, so overall, usually it has to be some sort of prediction involved, yeah? तो उसको हम क्या कहते हैं? ऐसी simple prediction का simplest word क्या है prediction का?
Yes.
What's the simplest word? Interpolation or extrapolation? Yeah?
Not simplest.
Simplest नहीं है? इससे ज़्यादा simple क्या? मतलब हमारे fields में, right? So let's say you had this guy xn and you had its values x0, x1, x2, x n something, and you had to upsample it by a factor of 2. Yeah. So this is how we work with it. We say okay, xu0 is here. Yeah. This guy will take this value. Okay. Whereas xu2 will take this value. Okay. वो t/2 था ना, ये वो होने जा रहा है. यहाँ क्या होगा?
Average होगा तो.
That is one way of
No,
interpolating. Now different algorithms will interpolate differently. Yeah, but you do understand that you need a placeholder here. Placeholder की ज़रूरत तो है. So the first step we do is make zeros. आप क्या करते हैं, आप पास 100 डेटा पॉइंट्स आए हैं ना, अगर आप सैंपल करना है, आप उन 100 के दरमियान एक एक ज़ीरो डाल देंगे. ठीक है, they are placeholders. Then you decide how you're gonna fill that guy. The simplest way is to do a linear interpolation. Then you can do spline interpolations, and you can use AI to do the interpolation. बहुत सही फिर interpolation है. But overall, this is how it works out. And firstly, can I write this as an equation? Piecewise equation x n by 2. N is 0 plus minus 2 plus minus 4. Do you agree with this? I am saying the new signal x upsampled n equals x n by 2 when n is even. N odd के लिए क्या होगा?
If you are averaging, you write that.
So first you are adding zeros. Yes, ये पहला step है. First you add zeros. We call this zero padding. You are putting zeros in between. They are just placeholders. Now in the next step, you will replace these guys by some sort of interpolator. Yeah. Simplest interpolator would be to do an average of the one to its left plus the one to its right. Divide by 2. This is linear interpolation. Yes. So this way you can do upsampling. Okay. Now just a interesting question. So it's like this. Let's say you had this guy 1, if I can draw it correctly. So you have it at 0, 1, 2, and then this guy, and then let's say you had this discrete time signal. Yeah, you wanted to upsample it. What would you do? First you will create gaps between them. So this is at 0, and you make a 0 here, and you get one value here, you make a 0 here, you put a value here, 1 0 here, one value here, another 0 and 0. Yeah, these are the new zeros you have placed in. Okay, these are your zero paddings. Next, you replace this by the average between these. Yeah, and you get the upsampled version. यहाँ पे आपने इनका एवरेज डाल देना सबका, वो आपके पास almost again even with, in this case, with the linear one. So I'll just ask you one last question and then we can end this. If this is a system, ये system है this guy that gives you the value for the padded RAM. Yeah, this is a system क्योंकि ये operation कर रहा है कुछ. Yeah, it takes in this value and gives out this value. Yes. So is this system causal or not? Yeah.
No one
So I'm saying this system that generates this value looks like this. It gives you the middle value, let's call that the xm. It takes in one value before that and one value after that. Yes, and gives you a value there.
So it is depending on future values, so that's like a non-causal.
It's a non-causal system. Yeah. So if you are going to do upsampling like this, you will need to buffer some values. Okay, good. So we'll take a quick attendance. Then we are done for the day.